Let's start. Okay. Okay, still one. Another entering. Okay, we start first. So last time we're talking about some of the parameters from the hydraulic conductivity, meaning for the hydraulic conductivity, and after that we're talking about the storage coefficient. And storage coefficient is quite important, although that only exists for the transient behaviors. If we're talking about a steady state, we do not using the storage coefficient. Yeah, I forgot to mention. Maybe we'll go back to the equation part. Emphasize again. Emphasize the content. So in the quantum flow equations, we have the parameter, two parameters, meaning for the hydraulic conductivity and storativity. And these two parameters meaning control the quantum behaviors in the hydrogeological system. So if we ignore the storage coefficient, or if the storage is ignored, is able to be ignored, that means we're going to go back to the called steady state condition. So we will only have the hydraulic conductivity to control the whole behaviors. We don't need to consider the storage coefficient, or we do not have the storage effect. So one of the important things that when we're talking about the steady state, it does not means they do not have the time inferences. That means the time is infinity. So when time infinity, that means they will reach equilibrium condition. But for the reality, quanta still float. Okay, they are not stop the flowing. They still have the flow, but they have the flow in equal to the flow out. So they just gradually move. Okay, so they do not change like the head quantities. So let's read what we mean. The storage effect is ignored. So storage coefficient only exists for the transient state conditions. And we're talking that the storage coefficient is quite interesting because it provides the extra waters that we pump. So when we pump the waters in an unconfined system, most of the conditions are very easy to imagine because they just release from the pore spaces. So the waters is be drained from the pore spaces to outside or to your well, and we were able to collect the waters. But for a confined system, they will be a little weird because confined system, they do not have look like they do not have the water change. They do not have the water variations, but we still able to collect the waters. So from the researcher, they using two mechanisms to explain the behaviors we call compressibility of the matrix. That means the pore spaces be compressed, so the water be seized out, and the other could be the water have the expand abilities. So when you decrease the pressures, the water have the expansions, so the actual water can be provided. So this is the two mechanisms from the confined system. So as I mentioned, that if we take a look at the whole pictures here, in the confined aquifers, all the water is occupied in these spaces, but we have the imagined water levels. Okay, imagined water levels, they will have the decline result. That means the pressures in these systems have the declined phenomenon. But for reality, we are not able to observe this kind of decline. So one of the things that from geophysical surveys, I also asked them, some of the professors in hydrogeological survey, they mentioned they can use in the geophysical survey to assess the groundwater level variations. But I'm asking them, for this kind of conditions, they were able to observe because we will have the saturation and unsaturations. So they can use in the resistivity or some of the conductivity to assess this interface. It could be possible. But I'm asking them if their methods can assess this kind of behavior. Because you can see that the water do not change. What they change is only the inside pressure. So is the geophysical surveys able to detect that or not? They mentioned maybe not. Okay. So geophysical survey, they use it to survey the groundwater conditions. Commonly is for the unsaturation zone. But for the saturation zone, right now maybe not easy to detect. But I guess still possible to detect. For example, if we're using the gravities, the water amount could be vary. Like I mentioned, originally they become dense, but after they expand, maybe the water's amount, total amount, still decrease, or their density decrease, or their mass decrease. Okay, because if if we take a look the concept of the expansions, they could be originally they are very condensed. Okay, so after we release the pressure, they become expand, so they become not so dense, they become loose. Okay, a concept like that. So maybe their mass will changes due to the gravity change, due to the density changes. Although in the groundwater system, we always assume that the density, viscosity, and the other property is the same; they do not change. Okay, so that's for the assumption from groundwater hydrology. We do not consider the change for that. And if you would like to assess more completely, you need to consider the compressibility of the soil matrix and also the waters. They'll be more complete to describe the behaviors. But for the gravity term, also have further. So you need to consider the gravity term change. Not gravity term, we call the body force. Okay, the body force, they might be affected. Gravity is the same, but if your density or your mass changes, you also be affected. Okay, so they'll be quite complex if you'd like to assess more completely. Okay, so storativity we can use in the concept is you need to count the head, how much water release. So the concept will be like that, but we sometimes using the unique area. Okay, so we will obtain these kind of quantities. So the storativity, you can see that they do not have the unit cubic meter divided by cubic meter, so we do not have the unit. And the quantities for the confined systems is relatively small because I mentioned confined is mainly release the water from matrix compressibilities, compressions, and also the expand of the waters. And we can imagine that there could be quite slightly, not so large amount. Okay, and if we consider the specific storage, they can be written down like this. But yeah, you can just take a look by yourself or go back to record yourself. And we're using this equation to describing the confined aquifers storage. So SS, we call the specific storage. That contribute from two terms. Is alpha is the compressibility of the matrix, and beta W is the compressibility of the water. And it seems the water occupy only the pore spaces, so we multiply the porosity. So we'll be able to obtain the water's amount of the compression or expansions like that. And gamma W or rho G is the gravity unit weight of the waters due to the gravity. Okay, so you'll be able to obtain this quantity. And if you take a look at the compressibility of the waters, approximately this quantity 10 to minus 10, so you'll be able to know that this quantity is quite small. Okay. So although you multiply the gamma W here, but the quantity is still around 10 to minus 5, so it's also not quite large compared to the specific yield or the unsaturated zone. And for the unconfined systems, we can separate to two steps in early time and in the later time. In the early time, if the conditions is like the is the a kind of the undrained conditions, maybe like undrained conditions or like a confined conditions. So in early time, we were able to use in the storage coefficients from the confined system, and later time we were using the gravity drainage to describing the behaviors. So that means the storage coefficient can be combined from the specific yield and specific storage. But remember that in the physical equations, all the units need to have the same dimensions. So SY, SS, we know SS is 1 divided by meters, is the length. They have the unit of the length. So we need to multiply the length, and then we can eliminate the unit to become dimensionless. And this is dimensionless and dimensionless, so they will be able to be plus together. Okay, we call this is the specific yield and specific storage and combine them together to be the storativity or storage coefficient. And as we know that specific yield is ranged from relative largest, and this is for the unconfined system. So that's from the gravity generated, and they are highly related to the porosity. So the quantity is commonly from maybe 0.01, not 0.1. Okay, 0.01 to 0.3 because commonly the porosity is around 0.3. They could be higher, but not very common because when you have a higher porosity, they might imply that you have the silt and clay, and they are not easy to have the gravity generated. Okay, so for the unconfined, this quantity, for the confined, this quantity. So although we can write down them together, but we know that this quantity is relatively small. Okay, 3 orders smaller, and if you have very thick aquifer thickness, maybe they're still able to have the relative larger quantity. And compare with the SY values, commonly is 0.1 this order. So this quantity will be relatively small, and we will simplify them or eliminate this term, and we can only have the SY values. So in the unconfined aquifers, commonly we use in the specific yield, not using the specific storage coefficient. Okay, so this is the concept. And later content, I think I will escape because they try to combine another specific retentions. That's the residual part. So I think we already mentioned in the last semester. So if you don't understand that, maybe you can read by yourself. So the concept here is a very important part. From the original, this is the water content, or the kind of the if we use in fluid saturations, there will be a kind of the like a porosity concept. Okay, and this is the like a head. So this is genetic behaviors when you have the high waters, and then due to the gravity generated. And in the very beginnings, we can see that the water is not easy to release, but for a specific period of time, or you increase your suction head, you will be able to generate more waters. And this is the water content, they will decline. But at the end, they will be very, very difficult to generate the residual waters out. So this part we call that's the residual content. Or that could be retentions. We call it specific retention. Okay, so this is some of the informations for you. And the concept is that specific yield and plus the specific retention will be the porosity. So that's the concept that we mentioned. Okay, so very quickly summarize the parameter part. So natural geological material contains void and or pores. The porosity is a measurement of the volumes of the void to the total volume of the sample. And permeability is the measure of the ability of the material to transmit fluid. And hydraulic conductivity is the important physical properties of the ground flow in a microscope point of view. And Dawes equations, they have some limitations. So be careful that Dawes equation is not always obeyed for the system. And 2 main aquifer parameters is the transmissivity and storativity. This is for the aquifer properties. We use pumping test with the tight solution to estimate the quantities. Yeah, we are talking about how to do that in the later lecture. Okay, so very quickly review the parameters. Any question about this? And following, I will introduce the concept for the hydrogeological survey. In the very beginning introductions for the courses, we already mentioned a little bit. And following, I try to use an AI system to help me do some preparation and also combine with some of the materials together. Recently, university asked us to use in the AI system, like we talked in the very beginning. Not only the student learnings, they also help professors can use in the AI to help them prepare the material. So I try to use that, although just a little bit, not quite many, because some of the content is not complete. And in the future, maybe we can also use an AI to like generate some of the data for you to do the analysis. That could be more useful for prepare the materials. So following, I try to use in the AI to identify what's the concept for the hydrogeological survey, and what could be the issues we should focus, and what should be what's the content we should try to address. And it provides some of the comments and suggestions for the preparations. So we can take a look at what it suggests, but some content is a little weird, so I delete. And some part I try to combine further information together. Okay. So what is a hydrogeological survey? That's the system investigations used to understand the groundwater conditions and availability and also the behaviors. So from the system, as I mentioned, when we're talking about the hydrogeology, commonly it is not only the solid part, it will combine the solid and fluid together. And from most of the textbook, they do not separate the hydrogeology to be the solid. They just combine them together. So as I mentioned in the last talk, hydrogeology or geohydrology is sometimes they exchangeable, or even ground hydrology, they are exchangeable. So all of that could be combined together. So when I use an AI to help me prepare or to provide some of the comments or the material for hydrogeological survey, most of the content still include the free part and the solid part. So honestly speaking, it's not easy to separate it. So here it mentions that the system we're using the groundwater condition like availability and behaviors. And another part is that when we're talking about hydrogeology, most of the concept is from sedimentary concept. So the content will be mainly for the alluvial fan area or the plain area. It's not for the rock, not for the mountains. Okay, so most of the contents belong to the sediments. Okay, so I try to input some of the extra information inside. And for traditional hydrogeology, is mainly to find out water resources. Okay, so you can also see that most of the content is mainly for the groundwater hydrology and also the water resources issues. Okay, so we try to understand how much water they have and how the water can float, and even the qualities issues. The quality, like environment or the qualities, how if the water is suitable for the drinking or for irrigation, like that. Okay, it characterizes subsurface material and ground flow. Okay, so they have the solid subsurface material. So there's the solid part and also the free part. And integrate geology, hydrology, geochemistry, and geophysics. So commonly we will combine the solid and the hydrology. And commonly they will put the geophysics, geochemistry is what I input inside extra information. So commonly we are using the solid and fluid together. And for the hydrology is mainly for the what we call the physical part. Okay, this is the solid part, and this will be the fluid part. But there will be mainly for the physics. And geochemistry is we using some of the environment, or using ions, or using the isotope to identify what could be the source. I don't know if you are familiar with that. We're using geochemistry to identify the source, or how much percentage is combined from the different water sources together. And geophysics is very commonly used for the hydrogeological survey. That could be from the surface part, as I mentioned. We can use that to identify like a bedrock, where could be the bedrock, and where could be the sediment thickness. Because, for example, the seismicity surveys is commonly to identify like the beddings. So if you have very strong beddings reflections, you'll be able to provide the information for that. And some of the geophysical survey will be able to provide the content, like the clay content. They have the different response, so you will be able to detect the clay. Or you might be able to detect like the free part, free phases conductivities. If you have geothermals or you have some of the fluids, they will have high conductivities and you'll be able to detect that. Or low conductivity like a neighbor system contaminations. You might be able to identify who could be the low conductivity area. They might have the contaminations there. Okay, so the geophysics is very commonly used for the geological survey or hydrogeological survey. And they support the water management and also the hazard assessment. So most of the conditions, we try to understand the water part. We try to find out where could be the main reservoir for the water resources. So most of the geological surveys to find out where could be the potential site. For example, in the Africa areas, they do not have sufficient surface waters. So right now they know that the underground, they will have a lot of waters storage there. But where could be the suitable place to drilling the wells, and then you can gather the water, sufficient waters. So they need to have some of the hydrogeological survey to understand where could be the suitable place to put your wells, and then you can do the productions. So that's for the water management or water resources assessment. And hazard assessment, as I mentioned in the very beginnings, when we're talking about hydrogeology, there could be three main issues. One is the water quantities, how much water we can obtain. That's a very important part. And water quality, if the water is suitable for drinking or suitable for the irrigations. Industrial, they will require less standard, so they will be still okay. Okay, so commonly this two is very commonly used for the groundwater hydrology. And the third part will be the constructions. Okay, infrastructure or some of the buildings. If you like to assess, you try to construct buildings, you need to understand the hydrogeological conditions, balance the buildings or that area. So you, like if you want to have the basement, you need to pump waters out and you'll be able to construct your buildings. So you need to know the hydrogeological conditions. And then you can set up how many wells is sufficient to pump the waters out to decline your head. And you'll be able to control the basement. And even one of the cases is the water level is too high or they have the high variations. So if you assess the groundwater level is relatively lower and your buildings constructions, you do not consider sufficient loadings. And when the water level uplift, your building will be uplift. They become dangerous. So there will be a case in Yangmei area. They control building, but after the wet seasons, the building uplift. So they need to put the concrete to the basement to increase the loadings to let the system balance. Okay. So that's the problems. They do not consider groundwater properly, so they assess some of the hazards. And another could be soil liquefactions. If the water level is high, you will have high liquefaction potential. Okay, because shallow part, they have the shallow relative lower overburdens from the surface. So the loadings is relative less. We mentioned that the total stress, and they have two bearing. One is waters, one is the effective stress. So when your total stress is very few, that means your port pressures increase to a very relative less quantities. They can totally bearing your total stress. So you are easy to have the liquefaction. Okay. And another part is if you have the clay in the shallow depth, and then your water level uplift, not clay, it's 5 cent. And your groundwater level uplift, and then that area might have easy to liquefy. Okay, so if your material, so there could be two of that, the fine grained material and also the high water levels. And another, I mentioned that for the slope problems, slope stabilities, groundwater play a very important role for that. So commonly you also need to know the variation or the groundwater flow patterns in the slope areas, and then you will be able to assess if they have the high potential to assess, to influence the to induce the hazard or not, the landslide. And the final could be they can form the basis for the numerical modeling. And numerical modeling will be able to provide for different disciplines like water resources, safety assessment, hazard assessment, and even the management issue. All of that could be okay, or even transport, solute transport, or the contamination transport. So the numerical model will be more widely used. So that could be a tool to use that, but you need to have the complete geological survey, and then you'll be able to provide the basic, like I mentioned last time a little bit, the geological system, hydrogeological system, how it affected the result, numerical result. And the definition for hydrogeology study the interactions between groundwater and geological materials, include water movement, storage, and chemistry. So this is the AI provide, but you can see that most of the concept could be approached to the water resources issues. So storage is amount of the waters, how much water you might be able to obtain. And the movement will be how fast the water or how much water pump you can obtain. If the material is very fine-grained material, you cannot use in a very huge pump, or they'll be dry. Your well will dry, and your pump will burn. So you also need to understand how fast the water flowed. And chemistry is to assess if the quality is okay for the drinking or irrigation. Okay, so you can see that when they define the hydrogeology is meaning for the water resources. This is from the AI system to provide. Okay. And for the hydrology and hydrogeology, commonly when we're talking about hydrology, is focusing on the surface water processes, and they can also quite depend. Different disciplines they might use in different terminology. For example, hydrology, do they include the climate, weather? I don't know. Yeah, but for widely definition, hydrology should combine all of them together, like we call a hydrological cycle, right? Or sometimes we use in the water cycle. They have from the climate, rainfall, and the cloud, the rainfall, and infiltrate, and evapotranspiration, and have runoff, have the groundwater infiltrations, and recharge. So that depends. But yeah, if we do not define clearly, hydrology means the surface waters. It's meaning for the rivers, pond, runoff, like that. And hydrogeology will be meaning for the subsurface systems. Yeah, but right now, as I mentioned, sometimes it's not easy to distinguish hydrogeology or the groundwater system, although, yeah, they combine together is not easy. And the component of the hydrogeological system, there will be geological framework, ground flow, this is the solid part, ground flow, free part, and then there will be the chemical part. So ground flow will be the physical part, how it flowed, and chemical part will be the quality issues, and human activities. So like pumpings, if we have the pumpings, they will have the human activities in the system. Okay, so when we consider the hydrogeological systems, we have many three components we might need to consider is, okay, the solid, fluid, and then the fluid is also separate to the physical part and chemical part, and then the others, the other factors, or like the human activities, how it affected the system. And the objective of the hydrogeological survey can be separated like several points. So the first part is provided by AI. Okay, the water resource evaluations. As I mentioned, that most of the hydrogeological surveys to support water resource evaluations, and a second part will be the engineering support. As I mentioned, that when you would like to construct the underground systems, you need to pump waters out, and then you will be able to have suitable engineering constructions, and even the tunnels. I think some of the local students will know that we have the Shih-Jung Mountains tunnels, and they have a very huge amount of the water drainage conditions when construct the tunnels. So it takes much longer time to finish the tunnel for that. So how to generate the waters to support engineering work is very important part. And as I mentioned, that water resources is mainly to collect waters for the usage. But for the engineering support, commonly is to prevent the waters. Water become the problems, so we try to remove the waters. So there's a different concept. And hazard mitigation is mainly like liquefactions or the slope stability. I think these two could be the two parts for that. Although some of the liquefaction could be a little bit connected, and some of the calf, like a road, some part you have the calf problems, and it is also affected by groundwater system, or sometimes the nature groundwater, sometimes the human activity. Okay. So not easy to distinguish. And the fourth part will be environmental protections. Although it's not easy to understand this part, but for example, we say that there will be the best flow concept. The best flow is from the groundwater outflow, commonly in the mountains area. So in the dry season, we can see that the river do not have the river have the waters, but we do not have the rainfall. So like recently, I don't know, maybe local student can see can watch some of the news reported that these years we might have the very dry conditions. It's a 75 years dry conditions because the rainfall is not sufficient in the western Taiwan in these early years. So from November to the May is the meaning for the dry season in Taiwan. So right now it's the March, so we still need to March, April, May. So we still need to keep 3 months for the water's conditions. So right now the water is not sufficient. We do not have that much rainfall to supply the western Taiwan. But when you go to the river, relatively big river, you're still able to see the water outflow. We still have waters there, so they come from we call the best flow, and they are drainage from the groundwater system to the river channels. So these kind of groundwaters will be very important for the environment. If you do not have the waters in the dry season, the animals in the river will die. Okay, like fish or some of the others will die. So this will be one of the important issues. And right now in Taiwan, maybe not so completely, but some of the places they will try to collect the groundwaters to fill the river to keep the we call the 激流, 生态激流量. I don't know how to 生态激流 ecosystem best flow. Okay, like that. We need to keep the minimal water flow to prevent the ecosystem to be damaged or to be broken like that. So sometimes we pump the waters to fill the rivers to protect the environment. So they might be one of the possibility that they can be connected to the environmental protections. Although it's not easy to directly connect it. Okay? Yeah, and some of the places maybe they have the like plant. You need to keep the plant. They connect to the groundwater system. And furthermore, as I mentioned, this one would be, when we're talking about hydrogeological survey or hydrogeology, is mainly for the relative shallow or the sedimentary areas. But for another, if we take a look more widely definitions for hydrogeology, they can include the rock system or the deeper systems. Okay, if we include that, some furthers could be, we doing the hydrogeological survey is to understand or to estimate the energy resources, like we know that geothermal, okay? But this is mainly for the rock. Although some of the places, they might have the hot waters is in a sedimentary area, like a Jiaoxi area. Although the source is from the rock system, but the main exploitation area could be in the sediment area, okay? And another could be the heat pump. Heat pumps is also relative shallow. They could be hundreds meters depth. We using the groundwater to be like a kind of air conditions, because the groundwater is relatively stable for the temperatures. So in the winters, we can use in the groundwater to warm up our room. But in the summers, we can use in the groundwater to cooling the room. Okay, so we call it a heat pump. They can use in the system to pump groundwater and then have the circulations in the room spaces to control the temperatures. Okay, that's for the energies part. And carbon dioxide sequestration or carbon sequestrations. We also know that we try to, recently in Taiwan, we try to develop several sites to store the carbon dioxide. They can decrease the carbon dioxide, or the carbons, and they are able to meet the net zero, okay? Although, I don't know is that good or not, but yeah, right now we try to do that. And carbon sequestrations is from the end part. We try to take the carbon dioxide and store in the subsurface. So we need to understand the geological structures. We need to understand if the seal system. We need to understand if they have the fracture or the fault to release the carbon dioxide or not. So we also need to do some of the geological survey or hydrogeological surveys. Okay. So that's a deeper system. Okay. And another could be the waste disposal assessment. Commonly is for the safety assessment, and that could be the nuclear waste, or some of that is like a backfill or the landfill. They have some waste, normal waste. They can also have these kind of conditions, and we need to prevent like they might have the leakage. So we need to find out like commonly if that's the landfill area, we need to find out if the material is the relative impermeable materials. So if we have more clay or the mud, they'll be better to construct this kind of disposal site. And for the nuclear waste, we need to find out like a crystal like system, rock systems, like granite in Taiwan. We try to find out the granite for the nuclear disposal system. Okay, but yeah, we need to do some investigation. Like we need to understand if the area have the high fracture system and high permeability system, or do they have the groundwaters there or not? We try to let the groundwater to be few, do not have the much. So we need to do the drillings to do the survey. And even we need to assess the fracture systems. Do they have the fracture or not, or how density of the fracture system? And if the rock space is large enough, or if they have some activity together, like if we have a fault, there will be a preferential flow path. They might release the nuclear waste. There will be the problem. So yeah, these several could be relative deeper or approach to the rock system. So commonly when we're talking about hydrogeology, we do not include that, but for the widely definitions, maybe we should combine them together. And the key questions in hydrogeological surveys could be like this. Also the same, the previous part is provided by AI. So where is the groundwater located? We try to find out where could be the main reservoir, groundwater reservoir for the water resources, okay? And how fast does it move? So we need to understand, like I mentioned, pumping abilities. Is the extraction sustainable? Is they have sufficient recharge? When we would like to consider the water resources, we know that groundwater system is maybe not isolated, but it's like a reservoir. So we have the recharge and discharge. If your recharge and discharge become equilibriums, and there will be no problems, they will be more sustainable to be used. So commonly when we would like to assess a reservoir is suitable or not, we also need to find out if they have the sufficient recharge rate or sufficient recharge source. If the reservoir is only have the reservoir isolated, when you pump waters, they become dry and there will be the big problems. Yeah, although in some places they dirty take the water, they don't care about too much. They don't care about the replacement. There will be problems for that. But for the sustainable usage, I think the extractions sustainable will be a very important part. So we commonly need to have the suitable pumping managements, pumping quantity management, how large pump you can use. And then water quality accessible, yeah, as I mentioned, for irrigation or drinkings, we need to confirm if the water quality is okay or not. Some of the water's nature conditions, they have the arsenic. So some of you might know that arsenic, that could be toxic, that will induce the cancer. So in Taiwan in the past, we have some places find out the arsenic, like mainly for the western or the coastal area. And arsenic is a very, not interesting, but a very abnormal. It exists in the natural system, but normally it do not have the toxic conditions because there's the oxidation conditions. The environment, they have the aerobic and anaerobic conditions. Okay, and in some of the conditions, they will change their ions format. I don't know how to say in English. Yeah, but they will change their system, like their 带电, their ions. I don't know how to say that chemical part. I'm not familiar with that. Yeah, so they will change their format. And if you, originally they will be safe, but after you pump, you induce more oxygen inside the system. So they change their environment, and then arsenic release, or they change it to another toxic format. And after that, the waters have the contaminated conditions. So arsenic in the nature is very common, but some of the format is toxic, some of that is not. And if you change the environments, you might release the arsenic. Okay, so in Taiwan, some places like Pingtung area, Pingtung Plain have that, and Zhoushu River have that, and Yilan County have that. And they are mainly from the clay material. So if you have clay, you need to be careful if they have arsenic compounds inside. Okay, so the water quality is also a very important part. Okay. And furthermore, this is for the water resources, but for the hazards or for some engineering systems, we might also need to understand the pore water pressures. Okay, so I state that if pore water pressure is sensitive to some of the conditions like rainfall, if you ever try to understand or try to take a look at the groundwater observations, you will see that the groundwater level observation, groundwater variations could be very largely. And some of the places, they are more sensitive. Some of the places is not so sensitive. Like in Taoyuan area, Taoyuan Zhongli tablelands, when you have the rainfall cannot directly infiltrate or recharge to the groundwater system. So the groundwater level variations in Taoyuan area is very slightly, very smoothly. They do not have the larger variations. But in the Zhoushu River alluvial fan, you will see the groundwater level observations. They have very largely. They can 20 meters variations. So in the wet seasons, they increase, and in dry season, they decrease. They could over 20 meters. And in some places in the plain area, or in the alluvial fan, from the proximal fan to the distal fan, the variation also differences. The proximal fan commonly is occupied by the relative coarse material, like gravel. And this kind of material, commonly the variation of the groundwater level will be very huge. Okay, because the pore space is large, so it will be easy to drainage out and also to recharge. And we're using the storage coefficient to describe this kind of behavior. So we can say that they have the very larger storage coefficient like that. They're easy to have the drainage behaviors. Okay. So if you have very high variations, you need to be careful. For example, I mentioned in the Yangmei case, they do not consider the variation for the groundwater levels. So when they do for this kind of engineering work, commonly they drilling a geological borehole, and they take the core sample and they will measure the groundwater level at the same time. So commonly they will measure the groundwater level and use the quantities to assess or to calculate like effective stress or to calculate the stress of that area. Okay, but if you don't know the hydrogeological conditions, they can vary, as I mentioned. If they vary 20 meters and you measure in the dry seasons, and then you might ignore, they might have 20 meters uplift. So you will underestimate some of the conditions. Okay, they become very dangerous. But in some of the places, the variation is very small, so every time you measure is okay. But if you do not have any sense to understand when you do the measurements at that time, that point, it will embed in very high uncertainty. For the engineering work, commonly they do not have the continuous management for the water level. They just measure that time, just one time. So maybe sometimes they measure 2 times. Okay, they totally using the quantity, the water level, to do the calculations, and it is not correct. You need to understand the background variations. Yeah, but honestly speaking, right now it's not easy because they commonly do not have the continuous measurement. But at least you can try to assess like what's the geological material or hydrogeological materials when you take the borehole data, when you take the core samples. You can take a look at the conditions. If they occupy by gravel or core sands, maybe they imply they will have high variations for the water levels. And you can also take a look at the time when they do the managements for the water levels. If they are in the dry season, you need to be careful because they will uplift in the wet seasons. Okay, so you need to understand the sensitivity for this kind of conditions. If they are easy to have the infiltrations, you have the heavy rainfall, ground level uplift very largely. Like our campus also have the buildings for 教研大楼. The basement, I don't know if you ever go to the basement, the parking lot, when we have the heavy rainfall, they have a lot of waters on the ground. They have the fractures. That means they have the high water pressures there, but the seal system may not completely. So we commonly can see a lot of the fractures, and they have the waters, groundwaters throughout. So they might not take too much of the care, attention for that kind of conditions. So the water pressures could be higher than their design or their constructions, I guess. And the same seasonal variations, if they have high variations, so you need to be careful. And another could be the excitations or the seismicity, like I mentioned, liquefaction issues. Some of the place, they will have the very slightly response. We call the Van strain sensitivity. We can use in the Van strain sensitivity or the strain sensitivity concept to assess if the site is very easy to be liquefied or not. If you are very sensitive to the seismicity for the groundwater systems, your water pressure increase could be very large, could be 1 meter. So that means when you have high seismic wave inside, you might have liquefactions occurred there. Sometimes we're using the side effect, but the side effect is considering the softness of the materials. And commonly we do not consider the waters, but be careful. We are doing some of the groundwater earthquake hydrologic conditions, and we can see that seismicity induced the water pressure change is very large differences in different places. And commonly for the CO system, like you have more fine-grained material like clays, your water pressure increase could be higher because they become like a kind of unchained conditions. And if you are the gravels, they are easy to change the water pressures, so you might not be able to accumulate the water pressures there. So be careful for these kind of issues. Okay, and how the hydrogeological materials or the strata distributed. This part is only for the water. Yeah, originally they using the groundwater investigation, but I think we're using the hydrogeological investigations. So you also need to consider the solid part, hydrogeological material, and also the fractal orientations for the rock system. The first part could be the sedimentary system, and the lower part could be the fractal system. You need to understand hydrogeological material because they affect quite largely, especially for subsidence. for liquefactions or for others part. Water resources may be not so largely affected, but the other could be. It depend on scale. And fracture orientations will affect it, like if you like to find a geothermal system, you want to store the CO2 layers, or you want to store your nuclear waste there. That will be very important for this several information for that. Okay, we take 10 minutes break first.